Okay, so here I'm going to give the algorithm which explicitly calculates those counts I was just referring to. And again, the main motivation for this is going to be that the EM algorithm is essentially going to be a variant of this algorithm. So as input we have a training corpus. And again, I'm assuming this idealized scenario where I do have the alignment on each training example. So each training example consists of an F, E, A triple. So FK is a sentence in French, and I'm going to assume M sub K is the length of the French sentence. EK is an English sentence. I'll assume L sub K is the length of that sentence. And then finally we have alignment variables A1 through AMK. Okay, so as one example we might have E100 is equal to the dog, F100 is equal to this, and then our alignment A100 is equal to, say, 1, 2, which basically corresponds to this alignment here. Okay. So the algorithm is going to iterate over the corpus, or run over the corpus, and calculate these counts. And then finally, the maximum likelihood estimates are just going to be simple count ratios. So TML of F given E is this ratio of counts. And similarly, the distortion parameters are ratios of counts. Okay, so let's talk about this inner loop where the counts are actually calculated. And so I'm going to pass over each training sentence in turn. And for each training sentence, I'm going to consider every possible French position, I equals 1 to mk, and every possible English position, 0 through lk. I'm assuming that the null word is also a possibility as usual. And I'm going to increment some counts. A critical definition is these delta variables. So k is the example number. I is a French position. And j is an English position. We're going to see these delta variables appear in a very central way in the EM algorithm, which we'll introduce next. But for now, these deltas are just defined basically as indicator functions indicating which alignments are present. So delta kij is 1 if the ith French word is aligned to the jth English word on this kth example. So let me illustrate this with this particular example. For this, we have delta 100 1 is equal to 1. Because French word 1 is aligned to French word 1 in English. Similarly, I have delta 100 2 is equal to 1. And then finally, delta 100 ij is equal to 0 for all other ij. Okay. So these deltas are actually quite simple. They just indicate which alignments are actually present. So this inner loop is basically going to iterate over all possible ij positions, and it's going to increment some counts. So let me actually, if you trace it through, you can trace through which counts are actually incremented on this particular example. So if you go through things, you'll find that C of the lur is equal to C of the lur plus 1. That's one increment. And similarly from this line, we're going to get C of the is equal to C of the plus 1. And down here, we're going to get C of 1 given 1, 2, 2. So that's the length of the two sentences. It's going to be C 1 given 1, 2, 2 plus 1. And finally, C 1, 2, 2 equals C 1, 2, 2 plus 1. Those are all the counts which are incremented based on delta 100 1 being equal to 1. And then we have a second set of counts. You're going to find that C of dog, chien equals C of dog, chien plus 1. C of dog equals C of dog plus 1. And there's a couple more counts here. So actually 8 counts in total will be incremented for this particular training example. And you can see that all this is basically doing is, in a rather laborious way, making sure that the counts for the correct items, for example, for there aligned to ler, are incremented on this particular example because there is aligned to ler. Okay. So, just to recap, this is meant to be sort of a very explicit description of the maximum likelihood estimate parameter estimation method. We end up with maximum likelihood parameter estimates under this very strong assumption that we know the alignments on each of the training examples. So the EM algorithm is actually going to be closely related to what I've just shown you. But recall that we're now going to assume that the training examples do not have alignment. So each training example is an English sentence paired with a French sentence. We again have n training examples, and critically the alignments are omitted. So the EM algorithm is going to take this input and again output t and q parameters as its final output, but it's going to proceed in a slightly different way. So the first major difference from the algorithm I just showed you is that the algorithm is going to be iterative. We're going to start off with some q and t parameters. For example, the first iteration, they might just be random parameters. Okay, so we start off with some random initialization. And then at each step, we're going to use these q and t parameters to calculate counts. In a moment, I'll describe how we do that. And so we're going to calculate counts actually based on, we have the data. This is the EK, FK pairs. And that together with our current guess at the parameters will give us some counts. And from those counts, we'll re-estimate the q and t parameters. So we're going to have an iterative method where at each iteration, we start with some values for q and t, and we calculate some new values for q and t. So in the next step, again, we're going to take these new qt parameters and take our data, and from those calculate counts, and from these recalculate our q and t variables. So we'll keep iterating like this until, in some sense, we've reached convergence. It's typical with these kind of models to run for maybe, I don't know, 10 to 20 iterations. It's fairly common for these IBM models. Okay. So that's the basic idea. We're going to have this iterative algorithm, random initialization, and then we recalculate the q and t parameters at each step, going through this process. And the only thing that's really going to change in how these counts are calculated is that, remember, our data doesn't include alignment variables. So instead, we're going to use our q and t parameters to actually calculate these deltas. So remember, we had delta k ij is equal to 1 if a k I is equal to j. Okay, so these were indicator functions making use of the alignment variables we had. Now we're going to replace these deltas with values that are actually calculated based on our current parameters in the data. And I'll, in a moment, talk much more about this way of calculating the deltas, how it's actually done, and what the intuition behind it is.